So we'll talk just a little bit about molecular shape. So to start with, we should talk a little about bond length. And bond lengths decrease as we go across a row. Because the size of the atoms decrease. But they increase as we go down a period as the size of the atoms increase. And bond angles are pretty easy in organic chemistry. If you remember this from VSEPR, valence shell electron pair repulsion, and that is that electron pairs want to be as far apart as possible. So because of that, if we have 2 electron pairs around an atom, the furthest they can be apart is 180 degrees. If we have 3 electron pairs around an atom, the furthest they can be away is 120 degrees. If we have 4 electron pairs around an atom, the furthest they can be away is 109.5 degrees. And we'll continue to talk about that here in just a second. And the problem is they don't make any sense with our s and p orbitals that we already know about. So let's start with carbon. So the electron configuration for carbon should be 1s2, 2s2, 2p2. Okay, so if I'm going to look at that, I'll draw some boxes. So here's my 1s orbital filled. Here's my 2s orbital filled. Here's my 2p orbital with the px, py, and pz. There's 1 electron here and 1 electron here. If you remember how bonds and reactions work, we need unpaired electrons. So if I were to look at carbon, let's call these px, py, and pz. Carbon has 2 unpaired electrons. And px and py would be at a 90-degree angle. So if I were to make a molecule out of carbon and hydrogen, I would guess that my molecule would be CH2 with bonds at 90-degree angles. So one would be used from the px orbital, one would be used from the py orbital. So I'd expect carbon to make 2 bonds at 90-degree angles. So the simplest molecule that's made up of just carbon and hydrogen would be methane. And let's pretend for a minute that we could make a crystal of methane. Methane's a gas, but and look at an X-ray diffractometer. What that will do is that will show us the position of the atoms compared to one another. And what we find out is that instead of this, carbon with 2 bonds at 90-degree angles, methane is actually CH4, and it has 4 bonds to hydrogen. And every angle is 109.5 degrees, or a tetrahedron. Now, what we know up to this point, that doesn't make any sense with our atomic structure. And that's where VSEPR comes in, because we started looking at hybrid orbitals. And so, before we start doing that, we have to ask ourselves, what are these orbitals? And really, all it is a mathematical equation. Pauling realized that if we combine all 4 of the equations for the 2s and the 3 2p orbitals, we'll find 4 new solutions that turn out to be equal in energy. N shape, and they only vary by their orientation in space. Which turns out to be 109.5 degree angles apart from each other. And the shape of each of the orbitals looks sort of like this. They're very directional. Almost all of the lobe is in one direction, with just a small lobe in the opposite direction. So if I only look at the major lobes and ignore the little small ones, what I end up seeing is something like this for carbon, where there are 4 major lobes and 109.5 degree angles from each other. And so, since we combined 1 s orbital and 3 p orbitals to make them, these are 4 sp3 hybrid orbitals. And since they're all the same energy, as we fill the electrons in, 1, 2, 3, 4 electrons in, none of them pair up, because up here, the reason that the 2s filled before the 2p is because it's lower energy. And so those ones filled first, and then the ones started to fill in the p. Since these are all identical energies, they don't pair up until they have to. And so that allows us to have 4 unpaired electrons. Now that we have 4 unpaired electrons, we would say that carbon makes 4 bonds, and each of those bonds is going to be at a 109.5 degree angle. And that's exactly what we see in molecules with carbon. 4 bonds at 109.5 degree angles. So that's evidence that this idea of hybridization is a good idea, because it's a model that explains what we see in real life. So if I have 2 carbons that want to bond with one another, and they will interact with each other in a head-on fashion, or head-on overlap. And we have head-on overlap, we call those sigma bonds. Don't confuse that with delta. Delta looks a little bit the same, but it's got kind of a little stem that's going up. Sigma is sort of a circle with a little line going to the side. Now, what happens with multiple bonds? Well, first of all, there can't be 2 head-on bonds between any 2 atoms. If there's a head-on bond, there's already a bond in that space. We can't put a second one in the exact same space. So the additional bond must be a different type of bond altogether. And in fact, any additional bonds after the first one have to be caused by parallel overlap of orbitals. And these kind of bonds then with parallel overlap are called pi bonds. Head-on bonds are sigma bonds, parallel ones are pi bonds. So if I have 2 carbons and we've got head-on overlap going this direction, that's our sigma bond. We can have an empty p orbital. It has to be a p orbital, so that would be perpendicular to that. We can have an empty p orbital that can have parallel overlap. So here's our sigma bond, and up here is our pi bond. Okay, but what happens to the hybrids if I use one of my p orbitals for the pi bonds? So if I have an s orbital, and px, py, pz, it doesn't matter which one you choose to use. If we use one of them for a pi bond, that one's not available to make hybrids for the rest of the molecule. So instead, all that's left is sp2. So instead of sp3 hybrids, we have sp2 hybrid orbitals. And those are characterized by 120 degree bond angles. Now, what happens if I want to have a third bond between these molecules? So there's one pi bond here, there's a sigma bond here. Where else can I put another bond? Well, it has to be perpendicular to to this first pi bond. So if I have a lobe coming out and going back, and a p orbital on each atom, now I can get a third bond, which is also going to be a pi bond because it's a parallel overlap. So to have a triple bond, I'll have a sigma, and then a pi, and another pi. Up here I had a sigma, and then a pi. All right, so if I do that, let's talk about hybrids again. So I have an S, I've got my 3 p's. I use one p to make the first pi bond. I use another p to make the second pi bond. And so that all that I have left now to make hybrids is one s and one p. So those are sp hybrid orbitals. And that's what's used to make the sigma bonds. There's an sp hybrid orbital here that's going to connect these two carbons. And sp hybrid orbitals have 180-degree bond angles.